Yes, the mechanical energy of the roller coaster is conserved because, as stated in the question, we are assuming that friction is not taking away from the energy of the cart. We are also not assuming that the cart is losing energy to other forms such as light, sound, heat, etc. Thus, we can assume that the cart will not lose energy to other forms and will only be transformed from gravitational potential energy to kinetic energy. The roller coaster cart is starting from rest at point A. Since the cart has a velocity of 0 meters per second at this point, all of the cart's energy is stored as gravitational potential energy. Thus, since we know the height of the roller coaster at point A, we know the mass of the cart, and we know the force of gravity, we can use the gravitational potential energy formula to find the mechanical energy of the cart. To find the mechanical energy at point B requires the implementation of the conservation of energy law. Since, as stated in the question, friction of the roller coaster is not applicable and there is no loss of energy to any other forms, the mechanical energy that the cart started with should be the same all the way down the track. Thus, the mechanical energy at point A will be the same at point B. To find the velocity of the cart at point B, we would need to use the kinetic energy formula, as it is the only formula that involves velocity in its requirements. As we learned in Part C, mechanical energy is conserved throughout the roller coaster. Thus, kinetic energy plus gravitational potential energy is equal to the total mechanical energy at any given point. Since we know the total mechanical energy from point A, this is the mechanical energy at point B. We know the height at point B, so we can use the gravitational potential energy formula to find out part of the total mechanical energy at point B. By subtracting the gravitational potential energy from the total mechanical energy, we can find out the total kinetic energy at point B. We can then sub in the kinetic energy found into the kinetic energy formula and then use simple algebra to find the velocity of the cart. To find the velocity of the cart at point C, we use the same process as point B. The only difference is that the height of point C is 0. Thus, the total mechanical energy is equal to the kinetic energy at point C, because the gravitational potential energy at point Z is 0 due to the height being 0. Now that the cart is starting with an initial velocity of 12 meters per second from point A, this means that the total mechanical energy at point A has changed. The total mechanical energy is now a combination of both gravitational potential energy as well as kinetic energy. The first step to finding the velocity at both points B and C is to figure out the total mechanical energy at point A, because the amount of energy will be conserved throughout the ride. After finding the total mechanical energy, we can then calculate each point separately. For point B, you must first find the gravitational potential energy at that point. You can then subtract the amount of energy from the mechanical energy to find the kinetic energy at that point. Once again, you plug this number into the kinetic energy equation and solve for velocity. Once again, we take the mechanical energy from point A and use it for point C. Since there is no gravitational potential energy at point C, all the mechanical energy is coming from kinetic energy. Thus, we sub in the mechanical energy for kinetic energy in the kinetic energy formula and solve for velocity once again.